The most basic form of an exponential function is f of x equals a number a to the x power, where the number a is positive. And from this exponential function, there are two different types of exponential functions. There are growth and decay functions. Now for a growth function, the equation is still f of x equals a to the x. But for it to be growth, we require that the value a is greater than 1, so that the quantity f of x grows as x grows. And for decay, the equation is f of x equals a to the x, but a is between 0 and 1. So the difference between the growth and decay from the function is looking at the number a, is it larger than 1 or is it less than 1? So for example, one growth function could be g of x equals 2 to the x. So in that function, the value a is 2, which is greater than 1, so that's a growth function. One example of decay is the function h of x equals 0.2 to the x. 0.2 is between 0 and 1, so that's a decay function. Another example is j of x equals 1/10 to the x. Because 1/10 is between 0 and 1, that is decay. So the graphs of growth versus decay functions look different as well. A growth function looks like this, where going towards negative infinity, the quantity of the function gets closer and closer to 0. Going towards positive infinity, the function increases. The graph for a decay function looks like this, where it looks similar to a growth function except that it's reflected across the y-axis so that it's decreasing. So as x goes towards negative infinity, the graph is going towards positive infinity. And as x goes towards positive infinity, the graph is getting closer and closer to 0. So both of these functions have an asymptote if they are unmoved. So if they're just of the form a to the x, we'll talk about translations later on. So they have asymptotes at the x-axis or at the line y equals 0. But growth is increasing exponentially, decay is decreasing towards 0 exponentially. Let's look at some examples. Determine whether each of the following represent growth or decay, then find f of 0 and f of 1. So we'll just recall that for growth, so we have function a to the x. For growth, we're looking for a to be greater than 1, and for decay, we're looking for a to be between 0 and 1. Okay, so this first function, f of x equals 3.2 to the x, that will represent growth because 3.2 is greater than 1. So now f of 0 would be 3.2 to the 0, which is equal to 1. And f of 1 would be 3.2 to the 1, which is 3.2. Example B, f of x equals e to the x. Now e represents the Euler number, which is an irrational number, 2.718, and then it continues but does not repeat. So since 2.718 is greater than 1, e to the x does represent growth. And e to the 0 is equal to 1. and e to the 1, rounded to 2 decimal places, is 2.72. And this is an approximation. Okay, now example C. Since we don't have the form a to the x, we have the form 10 to the negative x, let's rewrite this function. So 10 to the negative x, we could rewrite it as 10 to the negative 1 to the x, and 10 to the negative 1 is 1/10, so we can rewrite this as 1/10 to the x. Because a negative exponent means that we take the reciprocal. So since 1/10 is less than 1, this example represents decay, because 1/10 or 0.1 is less than 1. Now 1/10 to the 0 is again equal to 1, and 1/10 to the 1 is 1/10, or as a decimal, 0.1. Example D, f of x equals 2 to the 3x. So again, we would like to write this as the form a to the x, and we have a to the 3x currently. So to rewrite it in that form, we can change it to 2 to the 3 to the x, which means that it's equal to 8 to the x, since 2 to the 3 is 2 times 2 times 2, which is 8. Now this is growth, since 8 is greater than 1. And 8 to the 0, f of 0, is equal to 1. And 8 to the 1 is equal to 8. Okay, finally, example E, f of x equals 0.2 to the 2x. Again, we want to rewrite this in the form a to the x, so that means we consider 0.2 squared to the x. 0.2 squared is equal to 0.04 to the x. So this is representing decay, because 0.04 is less than 1. 0.04 to the 0 is equal to 1. And 0.04 to the 1 is equal to 0.04. So notice for these types of exponential functions where we just have the form a to the x, f of 0 is always equal to 1 when we have this form a to the x, and also f of 1 in this form is always equal to the base number a after simplifying in the cases of c, d, and e, so that we do have the form a to the x.